Thank you. My name is Filip, and today I'll be introducing you to private federated learning and some insights and innovations we've had within this subject at Apple. So the agenda for today is first, I'll be introducing you to the subject of PFL, and then I'll be going over open problems and challenges and different research areas and some of our solutions that we chose at Apple. And then lastly, I will be going over how do you get started doing research in PFL. Particularly, we have a newly open-sourced framework for doing simulations in PFL that might be interesting for you. So Apple strives to provide users with a high level of privacy, and users' data staying on the device itself is an important aspect of that. But how can you commit to such a value while still having to create more intelligent features learned from data? So there's the privacy aspect of this, and this is a general trend among customers that they are more privacy aware. And I see it's not supposed to be a question mark here, but some fonts are missing. But let's ignore that. And even if you overlook privacy, there's the regulatory aspect of this. So you might not be able to upload your data because of regulations like GDPR or HIPAA. And in the case of real-time IoT devices, they may be generating way too much data for the bandwidth available on these devices to upload, and then the data goes underutilized. And we all know that neural networks are data-hungry algorithms, and they simply perform better with more data. So first shown by Hesnes et al. In 2017, there's actually a very nice scaling law with this and on this log-log plot. And if you have data that are generated on devices, then you usually have much more data there than what you have uploaded to servers. And in the case of when users have evolving behavior, then if you are stuck with training a machine learning model on, for example, some open source data or some stale old data that you have server-side, or if you're constrained to just uploading from specific geolocations, then when you deploy your model again, then you suddenly do inference on a different distribution. So you want to train and do inference on the same distribution. And this is what private federated learning, it's a promising tool to solve these kinds of issues. And first, I will go through federated learning without the P, so federated learning, the name itself, you can see here the number of published papers that mention federated learning in the title has grown in popularity exponentially, as well as the interests of this in the industry. And I just see it continuing going forward. So what is it? The goal is to be able to centrally train. Well, the goal is to have a central model at the end that is learned from data without actually uploading data from the servers. So the data stays on the devices, and you get the final model on the server. So first, we have W0. We initialize that server-side. And then we randomly sample a cohort of users to send the model to. All of these devices independently do a local optimization procedure. In the case of neural networks, this can be multiple steps of SGD. And then the devices send backup statistics. And in this case, it is the model difference before and after local training, because this can be treated as a pseudo-gradient when averaged, and then you can update your central model to W1 here. And then you simply just want to repeat this procedure, sampling a new cohort of users And then after many iterations, then hopefully you'll have a good model server side. So this all sounds pretty simple, right? But when you do this in practice, there are a bunch of problems that arise that you haven't really accounted for. So I'm going to outline some of the problems that I, in my opinion, think are the most important ones to take a look at. The first one is privacy. So federated learning itself, it's not really privacy preserving, because like even if you don't upload the data from the user, you upload the gradients. And for example, here by Francesca Bonis et al., you can just use if you can inspect the gradients uploaded from the server, even if it's a batch of gradients, sometimes, or in many different use cases, you can actually do a perfect reconstruction and just recover what data these gradients represent. So yeah, that's not privacy preserving. And on the client side, there are more attacks that can be done. For example, a membership inference attack is where you learn whether a data point was included in the training or not. And in the case of, for example, training a model that predicts diseases, then you can imagine that the fact whether a patient was included in the training or not, that can be privacy sensitive in itself. Also, data poisoning is another attack where you as a client just construct adversarial examples and then train on that such that you can steer the model decision boundaries in the attacker's favor. And similarly, model poisoning specific for federated learning is when you do the same, but for the actual model difference payload that you upload to the server. And with this, you can create a so-called backdoor in your model. For example, given a specific 5 combination in the first pixels of an image, you can make it such that it gives a specific prediction. So how do you protect against this? First, to prevent anyone on the server from inspecting any individual gradient, the gold standard is to use cryptographical secure aggregation. So let's imagine we have 3 clients like this, and we have 3 data points we want to aggregate. So then you apply cryptographic noise on this data point before sending it up. And this noise is an integer, and it is the client's coordinate such that this noise that is added, when all of this is summed, then the noise cancels out. So it is decrypted implicitly in this sum. So then on the server side, you will just receive nonsense until all the participants have contributed, and then the true sum is revealed. So how to, differential privacy is another way to protect the model itself from attackers. So who here knows about what differential privacy is? If you can raise a hand. Yeah, so it's a very new concept, for many people, and I think this is very important going into the future. So I'm going to try and explain this here. Let's imagine we have a data set D, which has the data of different users, and then a data set D prime, where we just remove the data from one user. And then let M be a randomized mechanism that we can apply on the data. And if we apply it on D and D prime, we'll get 2 different distributions like here. And the difference here is due to removing one user. And the maximum difference between these 2 distributions is what we call e to the epsilon. And then we have, in the limit, also a difference called small delta. So now the definition of epsilon delta dp is a randomized mechanism M with domain D satisfies epsilon delta dp if for any two adjacent datasets, D and D prime, in the domain D, and for any subsets of outputs S in the possible outputs of M, this thing holds. So what this says is the output of the mechanism should not be whether you input a dataset D or a neighbor dataset D prime where only one user is removed. It should not be distinguishable by more than a multiplicative factor of e to the epsilon. So epsilon and delta are the privacy parameters that determines how much noise this mechanism needs to have. So a smaller epsilon means more noise. So how do you actually use this? So you can have a Gaussian as your randomized mechanism, and the thing that determines the noise is the standard deviation. And you can get the standard deviation as a function of epsilon and delta. So you specify a certain amount of privacy you want, and then you get the noise that you need to add. And this function f is very complex. There's a lot of research in differential privacy going on to sort of get better bounds for what epsilon and delta represent a certain amount of noise. And then using the central limit theorem, we know that a sum of independent random variables approximates a Gaussian. So you can actually distribute this noise and put it on the client side to sort of relax the trust model, so you don't have to trust the server that the noise is added. So you can read about our solution here in this paper by our teams, how we do it. And in summary, we have the data on the device. We add differential private noise to it. And then we have a secure aggregation method that we use where we split up the noised data into two shares. It's encrypted with two different keys. And then we have two different servers which are responsible for continuously aggregating contributions as they arrive. And when we have enough contributions, then it is implicitly decrypted. And with two servers like this, we can have a split trust model where only one of the servers need to be trusted to ensure that Apple only sees the aggregate. And this helper server, it can be run by some other entity. So an example use case at Apple that is currently deployed in iOS is iconic scenes, where we divide up the world into different areas. And within each area, we collect data of what kinds of object a person takes photos of. And then when you aggregate, well, and then we add differential private noise that I try to visualize here in yellow. So when we aggregate many of these vectors, then on the server side, it is revealed what are the different hotspots around the world where people tend to take pictures and histograms of what kinds of objects people take without revealing what any individual user, what they took a photo of. And this can be used to improve, for example, the map view in photos, where you can see a radical difference before and after the photo here suggested by wherever you took your pictures. And this was also later expanded for PFL to train a model doing this and suggest wallpapers for you. And this is also currently in iOS. So on the topic of data, it is actually very hard to learn a model when the data is partitioned the way it is in a federated setting. For example, the dataset sizes per partition can be very different. And the feature distribution per client can also be very different, as well as the label distribution. And then given the same label, it can be represented by different features. Or even the same features, users can label them differently. And to make it even harder, all of these distributions continuously shift over time because user behavior is changing. So to better experiment with this, on the server side, we published a dataset called FLAIR, which is a multi-class image classification dataset available here. And here we actually preserve the photographer IDs. So we're able to construct these sort of federated partitions with this dataset. So we have coarse-grained classes and 1628 fine-grained classes, so you can determine the difficulty of your task. And in this case, so we get these emergent properties of a federated data set. For example, photographers, they take different amount of images or photos. They have different cameras and camera settings, and they are interested in taking photos of different objects. And two photographers in two different parts of the world taking a picture of the same kind of object may look very different. Yeah, and there's a lot of research going on here on how do we better learn a model given these imbalanced partitions. And this is another 20-minute talk to go deeper into that. But if you're interested, you can take a look at this, what algorithms exist on your own. So another challenge is the communication cost. So the fact is that we have a central server, we want to learn a model there, but all of our data is distributed around the world, and the communication here is usually the bottleneck. So what we do at Apple, we try to do as many experiments as we can in a simulation environment instead. For example, trying out different features or tuning hyperparameters and stuff like that. So we are not constrained by the communication bottleneck. And to also make external researchers more productive with this, we have open sourced our simulation framework, which is entirely in Python, to do simulations with PFL. So why would someone use, why is PFL research needed? Which is the name of our open source framework. You have to experience this for yourself, but if you're researchers, we have very good interfaces to accommodate that, to accommodate you doing your research. And it's by far the fastest simulator out there. We support both PyTorch and TensorFlow, and we try to unify the benchmarks across these frameworks. And we can also add more frameworks if we need. And it's very well integrated with state-of-the-art privacy features. And we'll also support doing research with non-neural network models like GBDTs and GMMs, which is very underexplored in this area. And yeah, it should be very simple to get started with, hopefully. So what do we actually contribute? First, you're able to install our framework with pip install PFL. And we also contribute benchmarks on meaningful data sets. I don't have time for a hands-on tutorial on how this works, but this is sort of just an example of how a setup would work to run a PFL experiment. And just in line 0, you'll see that you can just use any regular like PyTorch model that you'll use in conventional machine learning. So how fast is it? We compared PFL research to other alternative open source federated learning simulation frameworks. And we recreated the benchmark, or C410 benchmark for these frameworks. Using just one GPU, we're able to converge a model in 4 minutes using PFL research. And we have 5 processes here just sharing the same GPU. FedML is the earliest open source framework, which is still popular today, and it's 28 times slower than PFL research. And then we have TensorFlow Federated, developed by Google. It's 27 times slower than this. And Flower, which is the currently the most popular simulation framework, it's very slow on GPU. When we scale it up on CPU, it's faster, but not close to PFL research. And then we have FedScale, which is another framework, still much slower. and Flute, developed by Microsoft, it's 20 times slower than PFL research. And looking at the GPU utilization, we can get ours up to about 90%, while many of the other frameworks, they struggle with the non-GPU overhead that federated learning brings. So that's a big problem. So here are two papers that used our FLAIR dataset with the original benchmark code that we published in TensorFlow Federated. And they complained that they didn't have enough computational requirements for this dataset to run the experiments that they wanted. So they could really have used PFL research because we did not experience this. So PFL research support both multi-machine, multi-GPU, multi-process training. And it's very scalable in that way. And instead of emulating the topology that I showed earlier with the in federated learning where you have a server and you have multiple clients and then communication back and forth, in a simulation, we don't need that. So we just have replicated processes and just one single efficient communication step, which is on all reduce, to sync model updates, metrics, and states between the processes. And then within each process, we have a scheduling to minimize the straggler processes. To compare the distributed simulations, we mainly focused on comparing with TensorFlow Federated and Flower, because those are the two most popular frameworks for publishing new research. And you can see here, once again, PFL research is much faster. So we also provide some official benchmarks with a framework that we think are realistic in federated learning. But first we have the C410 benchmark, which is mainly just for testing and prototyping. But we also have next door prediction on the Stack Overflow dataset using a light transformer model. We have our own FLAIR benchmark, and we have a speech recognition dataset, and this benchmark is still currently work in progress. And currently we have 3 different benchmarks for large language model fine-tuning with federated learning. And we also strive to provide this for both TensorFlow and PyTorch. So you can go to github.com on Apple's GitHub to PFL research, and if you're interested, you can take a look at our benchmarks and get educated in the documentation, or take a look at the notebook tutorials and give it a star. So that's all I had for today, so thank you for your time.
Thank you so much, Filip. And are there questions from the audience? I see a couple of, yes? Great.
Let's say we take your example with hospitals. Let's say the different regions in Sweden want to train a model based on the respective patient data in each region. And let's say I give you this task, and then you come back to me with a model. What would be the strategies or like for me to verify that you actually implemented this correctly? What would you say that I would do to sort of give acceptance? Is it trust the algorithm, or are there sort of methods or tools to sort of try to verify that actually no patient, I can't go back and find out that this disease or this is actually this patient in the model?
Yeah, so in terms of the cryptographic stuff, there are, well, what I showed that we have implemented, that there can be another entity that sort of delegates a bit of the trust in that this system is actually running and Apple cannot see individual gradients. And in the case of checking whether it has been trained with differential privacy, there are lots of research going on in auditing models. So you can search that up, like auditing differential private models, and there are techniques for checking what kind of privacy this was trained with.
Thank you.
Thank you. Do we have another question? I see at least one raised hand up there. If we can manage to reach them with a mic. Judith, it's very much up there. And unfortunately, we need to take it with a mic, otherwise we're not able to hear. Thank you, Judith.
Thank you. So I have a question. When you showed the use case for the maps, you were saying that you were like encrypting or doing the differential privacy with these zones or regions that you show into the map. But also in the piece of code that you show later, there was something that you were using the user ID to make this choice of which would be the level of aggregation that you will use to do this differential privacy. So the question that I have is that how do you decide which is the optimum unit of privacy? Like how do you decide where you will apply the differential privacy?
Yeah, so the best practices for what is enough privacy, that's still evolving and a bit subjective. I don't really have a good answer of that other than the industry or research in general converging on like this is the amount of privacy that you would need for certain kinds of training. In the case of the maps that you mentioned, this is using so-called local differential privacy, which it is a much stricter kind of differential privacy because we upload the raw statistics there. So we need more noise to privatize this. While in the case of training a model and uploading gradients, we can get away with a bit less noise. But determining what is a good enough privacy, that's a still very open question, which I don't have a good answer for.
Thank you. Thank you very much. May I ask a super quick question about open source? You mentioned the importance of it. Do you see the development and the adoption of PFL techniques possible without broader collaboration from the research community and open source tools and resources?
Well,
do you think there is a need for collaboration in this field in order to enhance the development?
Yeah, well, it's a very new field which requires a lot of tooling, and just because of that, people tend to, this research area is very working a lot in open source to together develop these tools because it's quite complicated to implement, and people and researchers need these tools which they take quite a lot of time to develop, so it's just a natural tendency for the community to work together to develop these tools. And I see it going much better for certain people or companies that do contribute to open source than other that keep things closed in this area.
Thank you very much. That's what I hoped for. And please accept these flowers from us. And please let's give an applause to Filip.